This video will present solutions to the VCE 2024 Mathematical Methods Written Examination 2, Section B, Question 1. Question 1 is initially concerned with the x-intercepts of the factored quartic f of x. Based on the null factor law, the solutions of f of x equal to 0 will be -1, -a, 2 and 2a. In Part B, we are asked about the values of a for which the graph of y equals f of x has exactly 3 y-intercepts. At first, this might seem a little odd, as we have just written down 4 solutions to f of x equals to 0 in Part A. Upon consideration though, for certain values of a, some of these solutions will be repeated. This will be when negative a equals 2a, or equals negative 1, or equals 2, or when 2a equals negative 1, or equals 2. This means we need to consider a values of 0, or 1, or negative 2, or negative a half. When a equals 0, the 4 solutions in Part A reduce to 3, with x-intercepts at -1, 0 and 2. Similarly, if a equals 1, the x-intercepts reduce to -1 and 2. If a equals -2, the x-intercepts are -1, 2 and -4. If a equals -a half, the x-intercepts are -1, a half and 2. Based on this table, the answer to Part B, Part 1 is a equals 0, -2 and -a half, as these are the 3 cases when the 4 solutions reduce to exactly 3 x-intercepts. The answer to Part B, Part 2 is all the other values of a, other than the 4 values considered above. In Part C, the focus is g of x, which is f of x in the case when a equals 1. With its repeated roots, the graph of g of x looks like this. To answer Part C, Part 1, I'm going to enter g of x into my class pad and differentiate it using the interactive calculation menu. By symmetry, I think the local maximum of this graph will be halfway between its roots, so at x equals a half, but I'll confirm this and find the y-coordinate of the local maximum by applying the fmax command to g of x, limiting x to values between -1 and 2. Based on what we know about the graph of y equals g of x, the answer to Part C, Part 3 is that g dashed x is greater than 0 for x from -1 to a half, the region from the left-hand minimum to the local maximum, and also from 2 to infinity, as these are the 2 regions of the graph where it is strictly increasing. Make sure you use round brackets here, as the question asks when g dashed x is strictly greater than 0. In Part C, Part 4, we are asked to consider the intersection of tangents to y equals g of x drawn at these 2 points. I'm going to use ClassPad to find these 2 tangents, first by dragging g of x into a new line, using the tan line command from the interactive calculation menu and making sure I carefully enter the first x coordinate. This output looks a bit messy, but tapping simp will simplify it. I'm now going to swipe that tan line command, pop it into a new line, then delete the negative sign from at the front of the root 3 to find the second tangent. I'll now find the x value where these 2 tangents meet by equating this answer to the previous one and solving. The answer of x equals a half may not surprise you, based on the symmetry of both the curve and the given points about the line x equals a half. With the x value in the equation of one of the tangents, the y-coordinate of the intersection point can be found, using that ever-useful given that symbol which can be found on the Math 3 keyboard. Part D introduces a function h of x, which has 4 distinct x-intercepts and a graph that looks like this. In Part 1, we are interested in translating the local maximum of h of x to the local maximum of g of x as found earlier. I'm going to start by finding the local maximum of h of x on my class pad. can now compare this point to the local maximum of g of x, which is at 1/2, 81 on 16. To translate 0, 4 to 1/2, 81 on 16, we need to translate h by half a unit in the positive x direction and 17 on 16 units in the positive y direction, as 81 on 16 minus 4 is 17 on 16. In part D, part 2, we need to transform h of x so its local minimums are the same as those of g of x. First, I need to find the local minimums of h of x. I'm going to do this by modifying the fmax command using the ABC keyboard. I don't need to alter the lower or upper bounds because the ones I chose previously include the local minimums that I'm looking for. As these local minima are root 10 apart horizontally, and the local minima of g of x are 3 apart horizontally, the first transformation required is a dilation by a factor of 3 over root 10 from the vertical axis. After this dilation, the leftmost minimum of h of x will be at minus 3 over 2, minus 9 over 4. To translate this point to the point minus 1, 0, being the leftmost local minima of g of x, next translate 1/2 a unit to the right and 9 over 4 units up.